So that's why we are working on learning a more general world model that can really just represent arbitrary things. So in this case, what we do is we have a neural network that can be conditioned on the past or other things to predict the future. And I mean, obviously, everyone has wanted to work on this forever. And I think with the recent rise in generative models like, transformers, diffusion, etc., we finally have a shot at it. So what you're seeing here is purely generated video sequences. Given the past videos, the network predicts some sample from the future, hopefully the most likely sample. And you can see that it is being predicted not just for one camera, but it predicts all the 8 cameras around the car jointly. And you can see how the car colors are consistent across the cameras. The motion of objects is consistent in 3D, even though we have not explicitly asked it to do anything in 3D or not even baked in any 3D priors. This is just the network understanding depth and motion on its own without us informing it of so. And since this is all just predicting future, RGB values, the ontology is quite general. You can throw any video clip from driving or from YouTube or from your own phone. Anything can be used to train this general dynamics model of the world. Additionally, it can also be action conditioned. We can show a few examples. So here on the left side, the car is driving in the lane, and we're asking it to, okay, just keep in this lane and keep driving. And then, like I said earlier, the car is able to, or the model is able to predict all of this geometry flow by very nicely and understands 3D. On the right here, we're asking it to change lanes to the right side. Maybe we'll go back and play it again. So on the left, it's just going straight. And we ask it to go straight, the model goes straight. And then on the right side, we ask it to make a lane change, and it makes a lane change. And the past context is the same for both of these outputs. So given the same past, and when we ask it for different futures, the model is able to produce or imagine different futures. This is super powerful because now you have essentially a neural network simulator that can simulate different futures based on different actions. And unlike a traditional game simulator, this is way more powerful because it can, represent things that are very hard to describe in an explicit system. I'll show a few more examples, but then it is super powerful, and also the motion, the intention, and then the natural behavior of other objects, such as vehicles, is very hard to represent explicitly, but in this world, it's very easy to represent. It doesn't have to stop with just RGB. You can obviously do this kind of future prediction task, not just in RGB, but also in panoptic segmentation, or you can extend it to also 3D spaces, where you can imagine future 3D scenes entirely based on just the past, and then your action prompting, or even without prompting, you can predict different futures. This is, personally, I'm amazed by how well this works, and it's a very exciting future that we are working on here. Yeah, here's some examples where I think something like this is going to be needed to represent what's happening in the scene. There's a lot of smoke coming in one of the pictures. There's paper flying everywhere. That's going to be tough for even occupancy, where you have paper flying everywhere. There's occupancy flow, but then how do you know it's paper? What do you know the material properties of it? There's smoke. Obviously, you can drive through it, but it is occupying space, and light does not transmit through. There's a lot of nuances to driving, and we have to really solve all of these problems to build a general driving stack that can drive anywhere in the world and be human-like, be fast, efficient at all speeds, yet very safe. And I think we're working on the right recipe for building this. And obviously, training all these models takes a ton of compute, and that's why Tesla is aiming to become a world leader in compute. Dojo is our training hardware that we have custom built at Tesla that is starting production next month, essentially. And with that, we think we are on the way to become one of the top compute platforms in the entire world. And we also think that to train these foundational models for vision, we need a lot of compute, and not just compute for training this one model, but compute to try a lot of different experiments to see which models actually work well. And that's why it's super exciting for us to, be in the spot where compute is going to be abundant, and it's just going to be bounded by ideas of engineers. The plot is this is not just being built for the car, but also for the robot. We already have the occupancy networks, for example, and a few other networks all shared between the car and the robot. And it actually works quite well and generalizes across these platforms. And we want to extend it to all the tasks that we have. Even like lanes and vehicles, for example, should not be specific to cars. If the robot, say, happens to walk to the road and looks around, it should understand roads and vehicles and how vehicles move, etc. All of this are just be built for both the platforms, and any other future robotics platform that would also need this. That's basically it. To summarize again, we're building this super cool foundational models for vision that really understands everything, and it should generalize across cars and robots. It's going to be trained on tons of diverse data from the fleet, on tons of compute. Yeah, so I'm really excited for the next 12 to 18 months of what's going to happen here. Thank you. Happy to answer any questions.
We have actually quite some time for questions. So if you have a question, you can come forward. Otherwise, I can start with one from the Zoom chat. And it's actually about the 3D reconstruction with your hybrid nerve approach. And the question there is, how can you actually deal with moving objects in this formulation?
We can really just track, moving objects. There's a lot of cues that the object is moving with respect to the scene, and we can also extract that information to segment moving things separately. Obviously, for things that we know can usually move, it's very easy, like vehicles, trucks, etc. Those are very easy because we already know that these objects can move. But arbitrary things such as flying trash bins or what have you, you can use a lot of other signals in the data itself to help do it.
Hi, yeah. Can you share a little bit more details about the world model? For example, is it similar to like VQ-GAN tokenizer and then autoregressive on top of those tokens, or mask-it, or any sort of details you can share?
I'd say still it's like work in progress. I don't think we don't have to over fixate on the current architecture. I think it's just the main message is that these kind of future prediction tasks are starting to work now, and that gives both like a simulator where we can roll out different outcomes, but also learn representations just by making this prediction. I think that is the key message.
Hi, thanks for the enlightening talk. I have a minor question. I really look into the details. I noticed that when you predict the lines or lanes, something like that, you use the autoregressive models. I wonder why is the logic behind this, the choice of autoregression instead of just simultaneously predict everything at once? Could you please illustrate the logic here?
Sure. Like you mentioned, lanes can like fork and merge and do other things, and there's a graph structure to them, and you can predict them simultaneously, and it's like hard to it is we want to model a distribution over high dimensional space, right? Because like if there's uncertainty on whether it's one lane or 2 lane, you don't want to predict 1.5 lanes. We want to either predict 1 lane or we want to predict 2 lanes. So we want a sample from the distribution. There's some distribution that okay, maybe 60% probability it's 1 lane and 40% probability it's 2 lanes. If you predict it without a proper generative model which gives nice samples, you will get sort of smear, and then everything will look blurry. And it's very hard to then use downstream. So that's why it's useful to, do something like this to get a nice sample.
Thanks for the great presentation. I have some questions regarding the technical details. So I want to take a look at the visualization of the occupancy network output. It looks like it's a 3D voxel. And I have a question about the actual voxel size, and do we change the voxel size in near field and the long range?
Yeah, again, these are like hyperparameters. Anyone can try with different voxel sizes. It's really a trade-off between memory and compute and what you're willing to do. So that these are not set in stone. It's not whatever the application needs. Even between the robot and the car, you can like configure different sizes, and they have different needs. So it is really configurable, and optionally can be made queryable, as in you can get like arbitrary position by just having the network emit small MLPs or something like that, where you can query to arbitrary position. Again, it just comes at compute. So it's up to the design of the downstream tasks to determine, what is the base size, you need these MLPs or not, and you get away with like some simpler formulations. It's really up to, there's like large design space here.
Thank you for the awesome talk, Ashok. So I have one question regarding the general model, word model you just mentioned. How would that actually apply to the humanoid task, for example, manipulation? What kind of methods you use to make that generalized from autonomous driving to the other humanoid robotics tasks?
Yeah, I think the same should apply for humanoid robot, in the sense that you can prompt it to do arbitrary things. You can ask it to pick up a cup, or walk to some door or something, and then the model should be able to imagine what picking up a cup would look like, or walking to a door would look like. And I don't see why it should be any different between the car and the robot. So because it's all pixels and the shapes are all the same, so it's just going to be a video that looks like the hand is reaching to a cup, or the robot, if it's a first person view, then it's a first person view of the robot, walking to the door. Like that's, I think it should work.
Okay, thank you for your presentation. You presented us a lot of individual modules. I would like to know if you could share us more details, how you will unify those modules into the end-to-end system in the FSD12. For instance, how the occupancy could be used in the end-to-end system.
Yeah, the occupancy is already used for a lot of collision avoidance. Sometimes when there's like some strange vehicles, say like there's construction vehicles that are, have their like lever arms, like going like this, and then can pick up things. And it's very hard to model using, say, cuboids or something like that, and you can obviously represent it with meshes, but then they become these high dimensional objects. Then distribution over them is pretty hard. And the occupancy is, like a slightly, I would say, low level or like a dumber task, where you can just like predict whether something is present and like where it is moving, and that is already enough to avoid collisions. And we make sure that the planning system respects collision avoidance from the occupancy.
Sure. Thank you for the wonderful presentation. I really enjoyed it. I'm very curious about your general world model. So I'm like a big fan of Tesla, and I want to know like what's like the inference times for this model. Can I expect to see it on a car anytime soon? Yeah.
Only thing I can say is that it hasn't shipped to customers yet, and we are still optimizing it. Maybe later this year. I don't know.
Oh, sorry. Yeah, I saw in your architecture you didn't have the map component fusion step in your model. Is it gone now, or if it's still there, then how do you deal with like alignment issue with your, because you're not using HD map, right? So when you fuse the map information with your perception information, like how do you deal with that in the fusion process?
Sure. Yeah, I think these are not HD maps, so the alignment is not super critical in some sense. You can have 20 meters of error or like 50 meters of error and still fine. It's really just what you would look at, at your phone or something when you use navigation. Your Google Maps or whatever map application you use might give you some route and like represent this, and that is enough to kind of tell the network where we want to go. So it's really like low definition maps. And it is intentionally designed that way so that we don't take a large dependence on the maps. It's really just to roughly guide which roads we should take, which lanes to pick and things like those.